All right, I'm back. We're talking about page 2 of note 6. Nope, page 2. What are we on? Page 2 of notes 8 of Calc AB. There's the landscaper showed up and they're doing like the post-winter cleanup. And so I don't know if the mic is picking that up at all. I guess I'll find out afterwards if I ever listen to the video. But so there's a rule that we can use if limits fall into a certain category. And that category is either of these things. Either we get 0 over 0 when we try to do direct substitution, or we get infinity over infinity. So if that happens, we have options. And we've already seen, like, there's some geometric stuff that we can do. There's some algebraic things we could do. There's like a very involved process if you're going to infinity or negative infinity, and there's radical involved. Let's see what we can do. So the concept is both of our functions are differentiable at x equals a. Why am I underlining when I could be highlighting like a boss? There we go. All right, so both of our functions are differentiable at a. And so this is a legacy thing in the notes. You're not allowed to do this anymore in Calc AB or BC. You're not allowed to do this. What you now need to do, so let me just write it out for you. You need to say that the limit as x approaches a of f of x equals the limit as x approaches a of g of x equals 0. So every once in a while, they make these sort of like arbitrary decisions. So we're not allowed to do this. So I'm actually trying to like cross that out as much as I can. What we're going to do now is this, right? So if we get that when we evaluate each of the limits, there's something we can do. So let's see what we can do. So if f and g are differentiable at x equals a, what else is true about them at that value? So if differentiable, so differentiable implies continuous. That's a bad arrow. Implies continuous. So as soon as they're differentiable, we automatically know that they're continuous at those points. Similarly, since they are continuous, and so continuous, and the limit as x approaches a of f of x equals 0 implies that f of a equals 0. And then also by the same exact logic, g of a is 0. So f of a and g of a are actually equal to 0. So we know a lot just because we know that the function is differentiable. We know it's continuous. If it's continuous, the value of the function equals the value of the limit. And we know the limits because we're presupposing that the limits are both 0. So we've got that. Tangent lines at x equals a. All right, so for f of x, our tangent line will be, so I'm just going to write y minus f of a equals f prime of a, and then x minus a. But I know that f of a is equal to 0, so I actually know that y is equal to just f prime of a and x minus a. All right, now why did I know that? I knew that because f of a equals 0. And then we can do the same thing for g of x. So for g of x, the tangent line, I'm going to do exactly the same thing just to like keep my flow. G prime. Oh, here comes the mower. I don't know if you can hear that. I kind of hope you can't, but I'd be amazed if you can't. Like, I don't really understand how this microphone works. I got it set up so it's maybe it's like cardioid mode or something if you're into polar. So I think it's only supposed to hear me, but like, how could it be ignoring that, right? It's like so loud. So this becomes g prime of a, and then x minus a. All right, and then this was true because we knew that g of a equaled 0, right? So we have our tangent lines. Now, the whole idea behind a tangent line is that when you are really close to the point of tangency, the tangent line is an amazing linear approximation of the function. You can basically replace the function with its tangent line. So if you are very, very close, there's no definition of very close, but limits always use very close. So if you are very, very close to x equals a, f of x is approximately its tangent line. So I'm going to just say that f of x is approximately f prime of a, x minus a. And then the same is true for g of x. G of x is approximately its tangent line. So g prime of a, x minus a. Okay, so if that is the case, then when I'm really, really close to a, I should be able to say that this limit is the same as the limit as x approaches a of our approximations, right? Just swap them out. F prime of a, x minus a over, not f again, g prime of a, x minus a. So this is just f prime of a over g prime of a, because f prime and g prime are just numbers. And we're basically done. So I really should have done one extra step with the limits because it's still indeterminate there. Limit is x approaches a, f prime of a, x minus a, g prime of a, x minus a. The x minus a should cancel. Should have done one more step. But you know what? This is just kind of like a proof, and it's a pretty informal proof to begin with. But we get this. So if we got 0 and 0 for our two limits, our respective limits. I got to stop saying 0 over 0. It's like really hard to break that habit. You do something for like 30 years, and then suddenly they're like, you can't do that anymore. Like, what are you supposed to do? So this is the case. Now, where are we getting f prime of a and g prime of a? It's because we're taking the limit as x approaches a of f prime of x, and the limit as x approaches a of g prime of x. So here is L'Hopital's rule. Also, on the AP exam, they put an S in there, the Hospital's rule. I say L'Hopital's rule. I think everyone says L'Hopital's rule, but I guess some people spell it differently, maybe. So L'Hopital's rule says, if f and g are differentiable, so I don't believe that you always need to state that, but it needs to be true. Differentiable in an open interval that contains a, that's fine. And you need this, so you're gonna write this part. Either you're writing this, or you are writing this. You need to write that though to get the full credit, and it's all about getting the full credit. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. It's insanity. And then if you get 0 over 0 again, do it again. If you get infinity over infinity again, do it again. You can do it as many times as you need to, provided you're always checking. You have to check the limits over and over again. Is the first limit 0? Is the limit of the numerator 0? Is the limit of the denominator 0? If so, L'Hopital's. And you can just keep going. So it's pretty crazy. I guess I should highlight like the actual rule also, since I'm highlighting everything else. So this is one, students love using this. Students actually love overusing this. So make sure you're not using it too much when you do these problems. But I'm gonna come back in the next video and actually start doing them. So I will see you in the next video when we're gonna do a bunch of problems using L'Hopital's rule. It's a very cool way of evaluating limits. And I'm pretty excited to do the problem. So see you then.